Let's apply calculus to the physics problem of a mass falling under the influence of gravity. We're on the surface of the Earth. This is like the original problem of Newton looking at an apple falling from the tree. So we have a mass. We can define an axis, a coordinate system. So we define the x-axis to be pointing upward, away from the surface of the Earth. Then we have a force on the mass pointing downwards. It's given by minus mg, where this g is 9.8 meters per second squared. So this is given physics. We apply F equals ma, so that gives us an equation for the acceleration. So the acceleration, which I'll write as x double dot, is equal to the force divided by the mass, which just becomes minus g. So the acceleration is a constant, and it's the mass is accelerating downward, so we get a negative sign. Our calculus now allows us to solve this equation. We can start integrating. We can use the fundamental theorem of calculus. So the integral of a derivative is just the function itself. So if we integrate the left-hand side with respect to time, then from the acceleration we'll get the velocity. If we integrate the right-hand side, we introduce a constant of integration, which we can call a, and then we integrate minus g, and that will become minus g times t. We can do one more integration. So the integral of x dot is just x. We get another constant of integration. I'll call that b. Plus we integrate a, we get at. And then we integrate minus gt, we get minus 1/2 gt squared. What are these two constants of integration? Well, if we set initial conditions, so say that the mass is initially at t equals 0, is at position x naught, and the velocity, or x dot, at t equals 0 is the initial velocity, which we call v naught. Then we can substitute into these equations. So at t equals 0, x is equal to b, so b is equal to x naught. And at t equals 0, x dot is equal to a, so that a is equal to v naught. So then we get our equation, which you might have seen before, is that the position as a function of time is equal to the initial position plus v naught times t minus 1/2 gt squared. So calculus, and particularly integration here, will allow us to solve for the position as a function of time. Let's look at an example. Let's say we have some building, right? Maybe the height could be something like 50-meter building, 50 meters tall. And we have some person on the building who wants to drop a ball down. So we can ask, how long does it take for the ball to hit the ground? Okay, so that's the question. So how do we figure that out from this equation? So we have to define our coordinate system. So let's define the coordinate system coming up from the ground. We have our initial position of the ball then, x naught is given by 50 meters, right? The initial velocity, the ball is being dropped by the person, so the initial velocity is going to be 0, okay? And then finally, the time it takes to hit the ground is going to be, I'll call that capital T, right? So at x, at capital T, we're going to hit the ground, so that will be 0. So these are our values of the parameters and the function itself for our hypothetical situation. So we can plug everything in. Let me just keep x naught there for now. So x of t equals 0, so we get 0 on the left-hand side, is equal to the initial position, which will be 50 meters. The velocity is 0, and that's minus 1/2 the gravitational acceleration times the time it takes to hit the ground squared. So we want to solve that then for capital T. It's easy enough. So we have capital T is equal to the square root, because it's t squared here. We have 2x naught divided by g. If we plug in the numbers, we would get 2 times x naught, so 2 times 50 meters, divided by 9.8 meters per second squared, square root. So meters divided by meters per second squared gives us seconds squared. So when we take the square root, we would get seconds. So it's about 100 divided by 10 square root, so about the square root of 10. This works out to be 3.2 seconds. Okay, so a ball dropped off a 50-meter building, neglecting air resistance. So this could be like a lead ball. So there's hardly any air resistance when you drop it. It will only take slightly more than 3 seconds before it hits the ground. If it was a feather, you would get a very different answer because the feather has a lot of air resistance. Let me summarize. We're studying a classical problem of the motion of a mass falling under gravity. We can solve that using F equals ma, as long as we know the calculus and we can integrate. Then we get this formula, which you might have seen before, that x as a function of time is x naught plus v naught t minus 1/2 gt squared. Now you know where this formula comes from. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.